Dear students, in this video we are going to study about electric field, important aspects of electric field due to the system of point charges, electric field due to continuous charge distribution, electric field lines and the rules to be followed, electric dipole and its properties, electric field due to a dipole, torque experienced by an electric dipole in the uniform electric field. And electric field lines. In this topic, we are going to study about the electric field produced by the charges and the electric field lines. Now, the first one is about electric field. The interaction between two charges is determined by Coulomb's law. How does the interaction itself occur? Consider a point charge kept at a point in space. If another point charge is placed at some distance from the first point charge, it experiences either an attractive force or repulsive force. This is called action at a distance. But how does the second charge know about the existence of the first charge, which is located at some distance away from it? To answer this question, Michael Faraday introduced the concept of field. According to Faraday, every charge in the universe creates an electric field in the surrounding space, and if another charge is brought into its field, it will interact with the electric field at that point and will experience a force. It may be recalled that the interaction of two masses is similarly explained using the concept of gravitational field in standard 11. Both the electric and gravitational forces are non-contact forces. Hence, the field concept is required to explain action at a distance. Consider a source point charge Q located at a point in space. Another point charge Q0, which is called as the test charge, is placed at some point P, which is at a distance r from the charge Q. The electrostatic force experienced by the charge Q0 due to Q is given by Coulomb's law, which is given by F is equal to K times Q0 by R square R cap. That's equal to 1 by 4 pi epsilon naught Q0 by R square into R cap. K is a constant that's equal to 1 by 4 pi epsilon naught. The charge Q creates an electric field in the surrounding space within which its effect can be felt by another charge. It is measured in terms of a quantity called electric field intensity, or simply called as electric field E. The electric field at the point P at a distance r from the point charge Q is defined as the force that would be experienced by a unit positive charge placed at that point P, and is given by E equal to F by Q0, and that's equal to K times Q by R square R cap. That's equal to 1 by 4 pi epsilon naught Q by R square R cap. Here R cap is the unit vector pointing from Q to the point of interest P. The electric field is a vector quantity and its SI unit is given by Newton per Coulomb, N c power minus 1. Now, what are the important aspects of this electric field? The first one, if the charge Q is positive, then the electric field points away from the source charge, and if Q is negative, the electric field points towards the source charge Q, and that is given in this figure 1.4. Here is the point P, and here is the charge plus Q. And this point, for a positive source charge, the electric field at P points radially outward from the point Q, from the charge Q. Similarly, if there is a negative charge, and for this negative source charge, the electric field at P points radially inward toward Q. So these two diagrams represents the direction of the electric field. Now the second case, if the electric field at the point P is given by E vector, then the force experienced by the test charge Q0 placed at the point P is given by F is equal to Q0 times E. This is Coulomb's law in terms of electric field. This is shown in the figure 1.5. Here there is a positive charge, and if this Q is positive, then the force on the test charge Q0 is directed away from Q. This is shown in this diagram. Similarly, if the charge Q is negative, the force on the test charge Q0 is directed towards Q. Third case, the equation 1.4 implies that the electric field is independent of the test charge Q0 and it depends only on the source charge Q. Fourth case, since the electric field is a vector quantity at every point in space, this field has a unique direction and magnitude as shown in figures 1.6a and b. From the equation 1.4, we can infer that as distance increases, the electric field also decreases in magnitude. Note that in figures 1.6a and b, the length of the electric field vector is shown for 3 different points. The strength or magnitude of the electric field at point P is stronger than at the points Q and R because the point P is closer to the source charge. Now, let us see these two diagrams. Here there is a positive charge plus Q, and here is a negative charge minus Q. The electric fields are moving away from this positive charge, and the electric field is towards the negative charge. Now the fifth case, in the definition of electric field, it is assumed that the test charge Q0 is taken sufficiently small so that bringing this test charge will not move the source charge. In other words, the test charge is made sufficiently small such that it will not modify the electric field of the source charge. Sixth case, the expression 1.4 is valid only for point charges. For continuous and finite size charge distributions, integration techniques must be used. However, this expression can be used as an approximation for a finite size charge if a test point is very far away from the finite size source charge. Note that we similarly treat the Earth as a point mass when we calculate the gravitational field of the Sun on the Earth. Now the seventh case, there are two kinds of electric field. First one is uniform electric field, that is constant, and non-uniform electric field. The uniform electric field will have the same direction and constant magnitude at all points in space. Non-uniform electric field will have different directions or different magnitudes or both at different points in space. Electric field created by a point charge is basically a non-uniform electric field. This non-uniformity arises both in direction and magnitude, with the direction being radially outward or inward, and the magnitude changes as distance increases. These are shown in this figure 1.7. Here this is a uniform electric field, and here is non-uniform electric field. So in the case of non-uniform electric field, we see this difference, uniform and non-uniform electric field. Next one, we will study about the electric field due to the system of point charges. Suppose a number of point charges are distributed in space. To find the electric field at some point P due to this collection of point charges, superposition principle is used. The electric field at an arbitrary point due to a collection of point charges is simply equal to the vector sum of the electric fields created by the individual point charges. This is called a superposition of electric fields. For this, let us consider a collection of point charges Q1, Q2, Q3, etc. up to Qn located at various points in space. The total electric field at some point P due to all these n charges is given by equation 1.6 and 1.7. Where R1P, R2P, R3P, etc. are the distance of the charges Q1, Q2, Q3, etc. from the point P respectively. Also, R1P, R2P, R3P, etc. are the corresponding unit vectors directed from the charges Q1, Q2, Q3. to P. Equation 1.7 can be rewritten as equation 1.8. For example, in figure 1.8, the resultant electric field due to 3-point charges Q1, Q2, Q3 at point P is shown. Note that the relative lengths of the electric field vectors for the charges depend on relative distances of the charges to the point P. For this, you can refer this diagram, that is given as superposition of electric field. Next, we will study about the electric field due to continuous charge distribution. The electric charge is quantized microscopically. The expressions 1.2, 1.3, 1.4 are applicable to only the point charges. While dealing with the electric field due to a charge sphere or a charge wire, etc., it is very difficult to look at the individual charges in these charged bodies. Therefore, it is assumed that charge is distributed continuously on the charged bodies, and the discrete nature of charges is not considered here. The electric field due to such continuous charge distributions is found by invoking the method of calculus. Next, we are going to study about the electric field lines. Electric field vectors are visualized by the concept of electric field lines. They form a set of continuous lines which are the visual representation of the electric field in some region of space. Following rules are followed while drawing electric field lines for charges. The electric field lines start from a positive charge and end at negative charges are at infinity. For a positive point charge, the electric field lines point radially outward, and for a negative point charge, the electric field lines point radially inward. These are shown in this diagram 1.9a and 1.9b. Note that for an isolated positive point charge, the electric field line starts from the charge and ends only at infinity. For an isolated negative point charge, the electric field line starts at infinity and ends at the negative charge. The electric field vector at a point in space is tangential to the electric field line at that point, and that is shown in this diagram 1.10. The electric field at a point P. Now, the electric field lines are denser, more closer in a region where the electric field has larger magnitude and less dense in a region where the electric field is of smaller magnitude. In other words, the number of lines passing through a given surface area perpendicular to the lines is proportional to the magnitude of the electric field in that region. This is shown in this diagram. So figure 1.11 shows the electric field lines from a positive point charge. The magnitude of the electric field for a point charge decreases as the distance increases. That means E is directly proportional to 1 by r square. So the electric field has a greater magnitude at the surface A than at B. Therefore, the number of lines crossing the surface A is greater than the number of lines crossing the surface B. Note that at surface B, the electric field lines are farther apart compared to the electric field lines at the surface A. No two electric field lines intersect with each other. So if the two lines cross at a point, then there will be two different electric field vectors at the same point as shown in this figure 1.12. As a consequence, if some charge is placed in the intersection point, then it has to move in two different directions at the same time, which is physically impossible. Hence, the electric field lines do not intersect. The number of electric field lines that emanate from the positive charge or end at a negative charge is directly proportional to the magnitude of the charges. For example, in the figure 1.13, the electric field lines are drawn for charges plus q and minus 2q. Note that the number of field lines emanating from plus q is 8 and the number of field lines ending at minus 2q is 16. Since the magnitude of the second charge is twice that of the first charge, the number of field lines drawn for minus 2q is twice the number than that for charge plus q. You can see this diagram. There are 8 electric field lines, whereas in this case, as the charge is minus 2q, there are about 16 lines.
What I wish I knew at school instead of memorizing formulas, field lines tell the story. They point the way a positive test charge would move, and once you see the pattern, problems get way easier. Electric field lines are imaginary arrows. They show direction of the electric field. They indicate field strength. They start on positive charges and end on negatives. Where lines cluster, the field is stronger. For a single point charge, lines radiate straight out or in simple and symmetric. For a dipole, one positive and one negative charge. Lines bend from plus to minus, revealing attraction paths. Rules to remember. Lines never cross density equals field strength. They show direction a positive test charge would take. Quick payoff. Instead of crunching vectors first, sketch field lines to predict forces and motion fast.